So when we're going to adjust the weight of this neuron, it's going to be actually quite different from adjusting the weight of this neuron. Now this is because you have two paths here. This neuron is affecting the first output neuron and the second output neuron. As you can see, there's a connection to this neuron and to this neuron. Therefore, when we're updating the weights for this neuron, we're going to have to consider two paths. This is the first path and this is the second path. Okay, so the path from the first output neuron and the path from the second output neuron, because this neuron is affecting both the output neurons here. So what we're going to do is we're going to apply the backpropagation, which is the chain rule here, to both paths. Okay, so remember, P here is the number of output neurons, and in our case, P equals to 2. So we're going to sum up the chain rule from this path and from this path. Okay, that's why we have a summation from j equals 1 up until p, and in our case p equals to 2. So we're going to sum up these two paths and then continue on with the backpropagation as normal. So let's start with the easy stuff. We have the derivative of our input with respect to the first weight. So this is easy to find. As I told you, the derivative of z1 with respect to w1 is just the input. So in this case, it's just x1, which we found is 0.5. Okay, so this is simple. And let's also calculate this, since it's also simple. The derivative of the sigmoid activation function with respect to your input. Remember, this is the formula for the derivative of the sigmoid, and when you apply it to your activation output, then you get 0.2484. Okay, so now let's talk about this right here. So what we want to do is sum up the path from this neuron and this neuron. So these are the two paths that we have. Now there's something different you should realize here. Previously, if I go back to the previous slide, when we were updating the weight for the output neuron, we had the third term in the chain rule as the derivative of your net input value with respect to the weight. This is when we were updating the weight of the output neuron. But here, we're actually updating the weight of the hidden neuron. So we only apply the derivative of the weight, derivative of your net input value with respect to the weight at the last step, which is here. But when we're summing the paths, then we need to take the derivative of the net input value with respect to the output of the hidden neuron right here. Okay, so we're going all the way to this path and this path. We're summing them up together, and then we're applying the derivative of the net input value with respect to the weight in order to update this weight. So we found these two from the chain rule, again, negative 0.1836 and 0.2031. And now here is the difference. So y1, if you take the equation of y1, which is the net input value to this output neuron, so it's going to be equals to w1 times 0.5399, which is the output of this hidden neuron, plus 0.4638, which is the output of this second hidden neuron, times w2, which is this red weight right here, and finally plus the bias, which is 0.31. So this is the equation of the net input value coming to the output neuron. Now we want to derive this not with respect to the weight, but with respect to the input. Okay, so the input of the first hidden neuron. Now what's the derivative of the input? In this case, if you derive this equation with respect to the delta Z1, which is the output of the hidden neuron, so if you derive this, then you'll end up with W1. Okay, so I rewrote this. When you derive Y1 with respect to delta Z1, you're just going to end up with W1. Okay, so this term right here is just your weight. This is exactly what we have. So this term is 0.37. Now let's take a look at the derivative of the error with respect to y2. And it's exactly the same thing, actually, but this time, this term is going to get cancelled out because there's no delta y2 2 in this term right here. So this is ends up going to end up being 0, and you're going to be left with this term. And remember, we said that the derivative of this term is negative of your error. Okay, so negative of your error, which is 0.4238 in this case. Now let's move on to the second term in the second path. Okay, so this is the derivative of your sigmoid activation function with respect to your net input value. Again, this is the equation for the derivative of the sigmoid, and if you plug in your values, basically we're doing exactly the same thing. However, we're just changing the values to the second neuron here. So when you plug in these values, you get 0.2494, and finally the last term, derivative of your input, but this time it's the net input value of the second neuron. So it's exactly the same as this equation, but rather than y1 we have y2. Okay, so in this case the derivative is w2. Okay, so that's exactly what we have right here, negative 0.22. Now multiply them all together and add them up, and you'll get the result of this summation over the two paths, which is negative 0.0370. And at the end, we're going to take this result, this result, and this result, multiply them all together, and you'll get your final gradient, which is negative 0.0045954. After we got the gradients, we can proceed to updating the weights. So we're going to take our old weight. This time it's 0.1. So it's the weight right here. The old weight is 0.1. And we're going to add it with the learning rate multiplied with the negative of the gradient. So the negative of negative 0.004 gives you 0.004. So at the end, you'll get your new weight as 0.1055. That's how you update the weights for the hidden neuron. And this is a nice reference or diagram to wrap it all up. If you're interested, you can visit this link right here, because this link really visualizes the concept of the backpropagation in a very beautiful way. Okay, so you can see that this is exactly what we said basically here. This is when you have only one path, and this is when you have two paths. So you're going to sum both paths together and then update this weight right here. So if you'd like to visualize more, then I'd really recommend this link right here, which visualizes the backpropagation in a very beautiful way. So a similar procedure will happen for all other neurons. Okay, so right now in this lecture, we basically updated the weights for this neuron and this neuron. Okay, so for the output neuron and the hidden neuron. So we updated these two weights. Now the same exact thing happens to the other weights. So after you do the same procedure for all weights, you're going to get these values right here. So these are the updated weights. Now this is, recall, this is only from the first sample. Now we need to proceed, of course, to the second sample. So if we're using, in this case, a stochastic gradient descent with a batch size of 1, that means we're doing weight update for each sample alone. So therefore, we're going to have 3 iterations in order to complete one epoch. So we take the second sample and then the third sample, and then we're finished with one epoch. So that's one epoch, and again we recall an epoch is one complete pass through all the samples. So after you repeat this for many epochs, usually in neural networks it requires from 25 to 60 epochs depending on your application, and it can also require more. It all depends on the application that you're doing. So after repeating this for many epochs, then the neural network is expected to reach the minimum error point and can be considered as trained. So we're going to talk about the optimization algorithms in a separate section, which we'll be discussing very soon. Thank you very much, and I'll see you next time.